Okay, so today we're diving into something that sounds like it's straight out of science fiction.
Mm-hmm.
I mean, seriously, Microsoft's new Majorana 1 chip.
Mm-hmm.
It feels like we're talking about a quantum leap forward,
Yeah.
not just like a little step.
Yeah.
And we're going to break it all down for you
Yeah.
right here.
Absolutely.
You're here because you want to understand the big things,
Mm.
the important stuff, quickly and thoroughly.
Yeah.
And our mission today is to cut through all the jargon
Right.
that comes with quantum computing
Yeah.
and really get down to why this chip is such a big deal and what it could mean for solving some of the world's biggest problems.
Yeah. Some really complex problems, things that we can't even really solve today. So we have a really fascinating news piece here. Microsoft's Majorana 1 chip carves new path for quantum computing. And as you can tell from the title, this comes directly from Microsoft.
Right.
And they're really highlighting two core innovations here.
Okay.
First, they've developed something called a topological core architecture, brand new.
Topological core.
Yeah. And the second thing is a breakthrough in a material that they're calling a topoconductor.
A topoconductor.
These two things are really at the heart of their effort to build much more reliable and critically scalable qubits.
So let's start with the basics. For a lot of people, I think quantum computing still sounds like something out of Star Trek.
Yeah, yeah.
What are the major roadblocks right now that current quantum computers are facing?
Well, the biggest challenge right now really lies with the qubits themselves.
Okay.
So you can think of qubits as kind of the quantum equivalent of the bits, the ones and zeros
Right.
that are in the computers we use every day. The problem is these qubits are incredibly sensitive
Oh.
to any kind of disturbance from their surroundings. So things like stray electromagnetic fields or even just slight changes in temperature can throw them off.
Really? Wow.
So this instability leads to errors, and those errors can very quickly corrupt the quantum information.
Oh.
It makes it really hard to do any complex calculations accurately.
So it's almost like trying to build a house of cards in a hurricane.
Yeah.
Like any little thing can knock the whole thing down.
Yeah, that's a great analogy. And that inherent fragility makes it really, really hard to increase the number of qubits that you can put in a quantum computer
Right.
and still maintain accuracy. So that scaling bottleneck is the fundamental challenge that Microsoft's aiming to overcome with this chip.
And that's where that quote comes in. Chetan Nayak called this a transistor for the quantum age.
That's right.
So what fundamental problem were they trying to solve when they were thinking along those lines?
So Nayak, along with the Microsoft team, they basically asked, what are the absolute must-have properties
Okay.
for a truly useful building block for a quantum computer? And they realized to move past the limitations of today's qubits, they needed something that was far more resilient to these errors, that wasn't so prone to being affected by noise, and something that could be manufactured and controlled in a way that would allow for massive scaling. So that transistor for the quantum age idea really captures the ambition to create this fundamental component that overcomes all those current limitations and can be used to build much larger and more powerful quantum systems.
And the foundation of this approach is this new topological core architecture. What
Yeah.
makes that design so important?
Well, what's really fascinating here is the potential to pack in a ton of qubits. So Microsoft is saying this architecture provides a very clear pathway to fitting 1 million qubits onto a single chip. And they really emphasize this is a chip that could fit in the palm of your hand.
1 million qubits.
So for someone like you who wants to really get to that core information quickly,
Yes. Yeah.
that kind of leap in density is a huge deal.
It's a game changer.
It really is, because right now, quantum computing designs are really struggling to even integrate a small fraction of that.
Right.
This new topological core is designed from the ground up to scale up massively.
Okay, so 1 million qubits on a chip that you can hold in your hand. It's mind-boggling.
Yeah.
And this is all thanks to advances in material science, particularly these things called topoconductors and the way they harness Majorana particles. So let's dig into that. What exactly is a topoconductor?
So a topoconductor, which is short for topological superconductor, it's a totally new state of matter.
Wow.
And the source material really emphasizes that it's not just another form of solid, liquid, or gas. It's something fundamentally different, this topological state. It's kind of like the surface of an object that has inherent properties regardless of its specific shape.
Okay.
And the really important thing here is that these materials have very special properties, particularly at their surfaces or their edges. And it's within these topological states that Majorana particles can be observed.
Okay, so a new state of matter.
Yes.
And we have these Majorana particles. What are they? And why are they so important for building stable qubits?
So they are a very peculiar type of particle.
Okay.
They're sometimes described as particles that are their own antiparticle.
Whoa.
Right. Very bizarre concept.
Yeah.
But this isn't just a theoretical curiosity. It's actually the key to this new kind of incredibly stable qubit. So the quantum information that's encoded in these Majorana particles is, in a sense, spread out
Yeah.
or topologically protected. So think about braiding information into the strands of a rope.
Okay.
If you just make a local cut to one strand, that doesn't destroy the overall pattern.
Right.
So that means that local disturbances or environmental noise are far less likely to disrupt that information. It makes the qubits inherently more stable and error-resistant at the hardware level. It's like hiding that valuable information in a way that's really difficult to accidentally damage.
So these Majorana particles, they don't just occur naturally.
Yeah.
You have to create them, coax them into existence.
Exactly. The source really highlights the immense effort that went into engineering the exact right materials needed to host these Majoranas. So Microsoft researchers, they actually developed this entirely new material stack that's composed of indium arsenide and aluminum.
Wow.
And they designed and fabricated the stack basically atom by atom
Wow.
to create very specific conditions. They need incredibly low temperatures, very specific magnetic fields interacting with superconductivity in order for these Majorana particles to emerge.
So that sounds like incredibly complex engineering.
Yeah, it is.
And the big payoff, they're saying, is the ability to scale up to 1 million qubits, which they're calling a really significant milestone.
Yeah.
Why is that million qubit number so important?
Well, they say that 1 million qubits is kind of that point where quantum computers can really start to tackle these really big problems.
Okay.
These meaningful problems that have industrial scale impact. And that really, speaks to what you mentioned earlier about the real world impact.
Right. Yes,
Yeah.
absolutely.
So the sheer computational power that you unlock at that scale could potentially solve problems that are completely out of reach for even the most powerful supercomputers we have combined today.
And they give some really interesting examples in the article. Things like being able to break down microplastics and even create self-healing materials.
Yeah. Yeah.
So let's talk about those a little bit.
So those examples really do illustrate the transformative potential. So imagine we could design catalysts that could very efficiently break down these vast amounts of microplastics
Right.
that we have now into harmless components.
Yeah.
Or what if you could have materials that could automatically repair cracks in critical infrastructure?
Oh, wow.
Like bridges or airplanes, or even everyday things like our phone screens or car doors.
Yeah.
So these are the kinds of revolutionary applications that become possible when you have that level of computational power.
And there's that quote from Nayak. It really drives this point home about the importance of being able to scale. He said, whatever you're doing in the quantum space needs to have a path to 1 million qubits. If it doesn't, you're going to hit a wall. So that really puts it into perspective.
Yeah, it really emphasizes that simply having more qubits isn't enough. You need the fundamental architecture and the ability to scale efficiently to really unlock the power of quantum computing and solve those complex problems. And the source really emphasizes that even if you combine all of today's most advanced computers together, they can't achieve what a 1 million qubit computer potentially could.
Another aspect of their approach is this idea of digital control of qubits. How does their new measurement approach simplify things compared to what's being used now?
So current methods for controlling and measuring a lot of the types of qubits we have today rely on these really precise and very individualized analog control signals for each and every qubit. So as you can imagine, as the number of qubits grows, that becomes incredibly complex and difficult to manage. Microsoft's new approach actually allows them to do digital control. Using voltage pulses, it's almost like flipping a light switch on or off.
Oh, okay.
So it's a lot simpler than this fine-tuned analog control that's needed for other types of qubits.
It sounds like it.
Yeah. So the simplification makes it a lot easier to build and operate these very large-scale quantum computers.
And all this progress is being seen as a real validation of Microsoft's commitment to these topological qubits. And it sounds like it was a pretty risky path to take.
Oh, it was definitely considered high risk,
Yeah.
but potentially very high reward. Because for years, these exotic Majorana particles were largely theoretical. So the fact that they've achieved peer-reviewed confirmation in a paper that they published in Nature, demonstrating that they can not only create these particles, but also reliably measure their quantum properties, is a huge validation of their approach.
And they're using microwaves to do that measurement.
That's right, yeah. So that's a major hurdle that a lot of other research groups hadn't been able to overcome. And that's one of the reasons why they've moved on to focus on different types of qubits.
And to add to that validation, Microsoft is also part of DARPA's US2QC program.
Yeah,
That really underscores the potential that they see in this technology.
absolutely. So their participation and the fact that they're now one of only 2 companies in the final phase of this program really speaks volumes. This is DARPA's program called Underexplored Systems for Utility Scale Quantum Computing, or US2QC. And this program is specifically focused on delivering utility scale, fault-tolerant quantum computers. So that means computers that can reliably perform complex tasks
Yeah,
and whose computational value actually outweighs their cost.
that makes sense.
Yeah.
And there's a quote from Matthias Treuer in the article
Hmm.
that I thought really highlighted the commercial focus of this project right from the start.
Yeah.
He said, "From the start, we wanted to make a quantum computer for commercial impact, not just thought leadership. We knew we needed a new qubit. We knew we had to scale."
Yeah, and that really emphasizes that this isn't just about making theoretical breakthroughs in the lab. This is about building quantum computers that can have a real impact
Yeah.
across industries.
Mm.
He goes on to talk about the potential for designing things right the first time,
Yeah,
which would be completely transformative.
it would be. And he talks about how that could be applied across a lot of areas like healthcare and product development.
Right.
What are some of the ways that designing things right the first time could revolutionize those industries?
So he basically suggests that a sufficiently powerful quantum computer could actually teach AI the language of nature,
Wow.
allowing it to give us the exact recipes for creating new materials or molecules with very specific properties. And that could eliminate potentially years or even decades of trial and error in R&D. So he says any company that makes anything could just design it perfectly the first time. It would give you the answer right away.
So the physical structure of this chip itself is
Mhm.
also pretty innovative.
Mm.
It uses this aluminum nanowire H architecture. Can you explain how that contributes to its scalability?
So the H structure is really clever. Each H is formed by these aluminum nanowires, and it hosts 4 controllable Majorana particles. And that whole structure makes up a single qubit. But what's really neat is that these individual H's can then be tiled across the chip in a very simple and repetitive pattern. So Christus War points out that once they've successfully created and can control a single H unit, the process of scaling up to huge numbers of qubits becomes a lot more straightforward. You're just replicating a single tile over and over again. So this tiling out approach promises a much faster and more manageable path to getting to that million qubit scale.
And it's not just about the chip itself. It's a whole interconnected system
Right.
that Microsoft has been developing.
That's a really important point. So the Majorana 1 chip doesn't operate in isolation. It's part of a much larger, very carefully engineered ecosystem.
Right.
So that includes the control logic to operate the qubits, a very specialized dilution refrigerator to maintain those incredibly low temperatures, and a comprehensive software stack that can seamlessly work with AI and classical computers. The fact that Microsoft has developed or modified all of these interconnected components really highlights how comprehensive their effort has been.
So with all of this coming together, the new architecture, the breakthrough materials, the digital control system, the scalable design, this whole ecosystem, where does Microsoft see the future of quantum computing heading?
Well, there's a lot of optimism in the source material. They say that this progress puts that million qubit goal within years, not decades.
That's amazing.
And Christus Foer raises a really interesting point about the long-term implications of this.
Okay.
She says our understanding of quantum materials right now is still very limited. And she suggests that these large-scale quantum computers will actually help us to design even better materials for the next generation of quantum computers. So it's potentially this really powerful cycle of innovation.
Okay, so let's break this down. What are the key takeaways from our deep dive into Microsoft's Majorana 1 chip announcement?
So I think the main takeaways are these. This Majorana 1 chip really represents a huge departure from traditional approaches to building quantum computers. And that's mainly because of its novel architecture, the topological core, and its use of these topoconductors to harness the power of those Majorana particles. This combination allows them to create qubits that are far more stable and far less prone to errors. And that, as we've been talking about, is absolutely essential for achieving that massive scalability that they need to tackle these big problems. And the use of digital control for the qubits and that modular H architecture further paves the way towards making that million qubit goal a reality.
So for our listeners out there, why should all of this matter to you?
I think this breakthrough gives us a very real glimpse into a future where incredibly complex challenges in all sorts of different fields. Materials, science, chemistry, medicine could be addressed with speed and accuracy that we've never seen before.
Yeah.
Imagine being able to accurately simulate and understand how molecules and materials behave at the quantum level. That opens up all sorts of possibilities.
Yeah.
Designing new drugs, creating more sustainable materials, potentially revolutionizing industries in ways that we can't even imagine today.
It's a profound thought. Considering this potential to design things perfectly the first time, what global challenges do you think could be most significantly impacted by the arrival of these million-qubit computers? And what new possibilities might we see that we haven't even thought of yet?
Yeah, it really makes you think about the massive implications of this kind of technology
It does.
and what kind of future it could create for all of us. I think it's a really exciting time to be following this. It feels like we're just at the very beginning of a really amazing journey.